2020 paper 1. I thought this paper was pretty good because of how it was asked. It was slightly different to the usual way. So that's why I wanted to do this. Okay, so multiple choice was around the same, but the actual long questions were a little bit different to what we were used to. So let's get into this. Okay, first up, question 1. It says Susan, who has a weight of 750, stands in a stationary lift on a bathroom scale, which is calibrated in newtons. The lift starts to move, and during the first part of the movement, the reading on the scale is larger than 750 newtons. So because they say the reading on the scale is larger than 750, this is something we need to know about Newton's third law and how it works, right? So this is part of the elevator lift questions. I'm not sure if you guys remember me explaining this last year. For those who were with me last year, I explained the following. I explained that in a lift, if you accelerate upwards, that means that your weight is going to increase. So let's say we accelerated at 2 meters per second upwards. We would say that our weight is actually going to be our mass. Just move that slightly down. It's going to be our mass, because the mass doesn't change, times gravity plus the 2, plus the acceleration, right? Plus the acceleration. Now, in the same sense, if we're accelerating downwards, at 2, then this would be minus 2, right? That's what we need to understand. So here it says, which one of the following combinations best describes the motion of the acceleration of the lift during this part of the motion? So please note, obviously, we should be going upwards. The direction should be upwards, and acceleration should be upwards as well, right? Because if we're moving upwards and accelerating upwards, we know that our weight is actually going to increase, because we kind of like define gravity in a sense, where we're adding on to how much of G force we should feel. Okay, so that's 1.1 done. Guys, if you have something you want to ask, please let me know. Also, I just need to find my phone somewhere. So I guess that's me dropping the phone. Anyway. Okay, so let me just see if I have any questions on WhatsApp. Yes, okay, so fair question. So the question is, what happens if it's constant velocity? So guys, here, if this whole thing is moving at constant velocity, whether it's up or down, then that just means that our weight stays the same. So our weight then here would just be mass times gravity, right? Constant velocity up or constant velocity down, our weight is actually not going to change then. Okay. All right. Here, it says an object is thrown vertically upwards. The velocity time graph below represents the motion of the object during the time interval 0 to 3 t seconds. Now, this one was pretty cool, because it brought into our knowledge. Well, it brought our knowledge of graphs of velocity time, displacement time in a multiple choice. So here they say that what is the magnitude of the resultant on net displacement over the 3 seconds, or over the 3t seconds, 3t minutes, whatever it is, right? So we need to know that displacement, resultant or net displacement, is always going to be top area minus bottom area. And remember, they just want magnitude, so they just want a value. Apologies, guys. Through the whole lesson today, I'm telling you guys, my nose is going to be crazy. Okay, so guys, here, when we're going to do this, this is going to be our area for the top. Right? That's going to be our area for the top. So I normally just indicate that by area 1. This is going to be the area for the bottom. That's area 2. So all we do to find the displacement, area 1 minus the area 2. So area 1 is going to be a half of my t times v minus a half of my, remember this would be t to 3t is basically 2t there, times the velocity of 2v. And then we just sort that out from there. So that's going to be a half tv, or vt, they put it as vt, minus 2vt, which is actually just equal to minus 3 over 2vt. But remember, because they want magnitude, because they're asking for simply magnitude, here we just have to give it as that. Magnitude is just value. So it's 3 over 2 vt. That's very important to understand, guys. Okay, that it's just, when they ask for magnitude, it is just the value. Okay. Guys, again, any point in this here that you guys are not making sense of, stop me, tell me, we'll go through it, yeah? 1.3, it says a ball is thrown vertically upwards. Which one of the following combinations of the physical quantities has non-zero values at the maximum height? Okay, so guys, here, ball is thrown vertically upwards, and they want non-zero values at maximum height. So now, first up, when something is at its maximum height, it's thrown upwards, we know that velocity is 0, so therefore kinetic energy would also be 0, right? If velocity is 0, kinetic energy would be 0. However, we would actually have some sort of potential energy, so potential energy will have a value, right? Potential energy would have a value. So here, let's go and see what other things would have a value. Obviously, what we would also still have, if it's some sort of object, let's put the object in purple, for example, let's say it's a box. The box would still have its weight. And remember, for any object that's in vertical or in projectile motion, they would still be gravitational force acting on it. There would still be a gravitational force of 9.8 acting downwards. So there'll be weight, there'll be gravity, and there will be potential energy. Okay, let's go and see which one of these make the most sense for us. Okay, so velocity, no. Momentum, no. Kinetic energy, no. Weight, yes. And acceleration, yes. So our option there is D. Immediately, our option there is D, guys. Is anyone with any questions on this one? Please let me know. No, seems okay. All right, guys. 1.4, it says the graph below represents the change in force with time for a tennis ball that is thrown towards a tennis player and struck by the player in the opposite direction. Okay. So what does the area under the graph, what would the area under the graph give us? Well, we know that the area under the graph should give us, because this is some version of force times time, right? So because this is going to be some base times a height. So what we have is time over seconds times force, right? That's what the area is going to give us. I shouldn't say time seconds, but it's time that is in seconds. That's what it should have been here. Time measured in seconds. So it's basically time times force. So time times force, which we would know as impulse. Right? We know that the F net times the time is equal to the impulse. So here, what is our actual impulse? Do they give us impulse as an option? Let me just see. Yes, B. Impulse experienced by the tennis ball. Now, I think one of you guys, actually not one of you, I think it was 3 of you guys, sent me something similar previously. And I answered it the same way. You guys, all 3 of you guys asked, why can't, when you're calculating the area, why can't I just say 150 times by the seconds there? Why can't I just say that? And why do I have to find the area under the curve to calculate my impulse? Well, because here, it is not 150 newtons acting consistently for 0.1 seconds. Basically, this is telling us that our velocity, our force is increasing to that point and then coming back down. So now we can obviously see that we're not having 150 newtons at this point. We don't have 150 newtons at this point. We don't have 150 newtons at this point. We don't have 150 newtons at this point, and then so onwards. So we have to find out what the area under the actual curve is to give us our actual impulse acting. Otherwise, we wouldn't be calculating it correctly. We'd be saying there's 150 newtons of force for an entire 0.1 seconds, but we can clearly see that's not what's going on. That's why we actually calculate the area under the curve, guys. Okay, now 1.5. It says the diagram below shows a track ABC. The curved section AB is frictionless. So that's no friction here. Nice. I'm pretty sure I've seen this diagram before somewhere. I can't remember from where. It says the rough horizontal section BC is 8 meters long. Fine. So we know there is friction here. It says an object of mass 10 kilograms is released from point A, which is 4 meters above the ground. It slides down the track and comes at C. Okay, so what's going to happen here? Here it says which one of the following statements about the mechanical energy of the 10 kilogram mass is correct if it loses energy along BC. Okay, guys, if we're losing energy along BC, it makes complete sense for us to lose energy here. I shouldn't put it in blue. It makes complete sense for us to lose energy here for B to C. And why? Well, because we know there's friction, right? So that means mechanical energy, I shouldn't say mechanical energy is lost, but there's going to be a decrease in the amount of mechanical energy here. The amount of mechanical energy here is going to be less than the amount of mechanical energy there, because we have friction on that side. We have friction here. So here it says the mechanical energy of the 10 kilogram mass remains constant from B to C. This is obviously nonsense, because they want us to find out what is the correct statement in terms of what's happening to the energy. So obviously it's definitely not that. It's not remaining constant, like we said. It says that mechanical energy at A is greater than mechanical energy at B. No, we said for this whole piece it should be remaining constant, right? Only here it decreases. So whatever the mechanical energy was here, it then starts to decrease until it comes to 0 there, basically, right? So here, let's go and see what's C's option. So C's option says that mechanical energy at A is equal to the mechanical energy at B. Yes, that's definite. So our mechanical energy at this point here, mechanical energy at this point must be equal to the mechanical energy at that point, because there's no friction acting on this piece. So mechanical energy must remain constant from A to B, guys. Okay, next up for 1.6, it says the pressure versus time graph below represents a sound wave in air emitted by a stationary source. Okay, so that's fine. Okay. It says which one of the following graphs best represents the sound wave as observed by a stationary observer if the source is moving away from the observer? Okay. So what you need to know is how fast this, let's put it in another color. Let's put it in, maybe better in red. So how fast this takes to complete one cycle is basically its frequency. So for example, if this looks something like this here, this will happen at a greater frequency, right? At a greater frequency. So we need to figure out, in this particular one, guys, we need to figure out, they tell us it's moving away. So here they tell us that if the source is moving away from the observer. Okay, so they want to find out which graph best represents the sound wave as observed by the stationary observer if the source is moving away from the observer. Now, guys, if we are moving away from our observer, what are we supposed to know? Moving away means that our frequency should decrease. It means that our frequency should decrease. So that means how often it happens should be less. So yeah, it should happen less often. So basically what we're saying is that it should take longer to complete one cycle, right? This is saying that it would take longer to complete one cycle. That's what it should look like, something like that. So here, which one best represents that? So it could be C or it could be D, right? And let me explain to you now immediately why it's not A and why it's not B. It's not going to be A because here it's saying that we have a greater frequency. We definitely don't have a greater frequency. For B, it's kind of decreased the amplitude. We haven't done anything with the amplitude. The amplitude remains the same. So therefore, it's definitely not B. Let's see for C, what is the amplitude here? Oh, amplitude was to the top there and to the bottom there. So that means obviously amplitude has not been changed, so that's why it's also not C. D makes the most sense because it's the same amplitude. It's just that now it's taking a longer time. So that means our frequency has decreased. So our only correct option is actually D. Okay. Guys, again, anything here that you guys want me to recap, please let me know, yeah? Oh, seems okay. Guys, 1.7, it says that the magnitude of the electrostatic force on charge 1 due to another charge Q2 is F. The distance between the charge Q1 and Q2 is R. One of the charges is now double, and the distance between the charges is halved. Okay, so it's a two-step process here, guys. That's all it is. It's a simple, easy two-step process. So force is directly proportionate to charge, and force is inversely proportionate to your R squared. So here we need to know that our radius is now halved, right? The distance is now halved, so it's a half R all squared. So this is going to be 1 over a quarter R squared, which means that if this is now a quarter R squared, this must become 4 now. So this is going to be 4F, right? Then on this side, they tell us that our charge is now doubled. Our charge is now doubled, so our force is now doubled. So here we're dealing with 2F, and here we're dealing with 4F. So it's just 2 times 4, which is then just going to give us 8F, and that's it, done. That's an easy one. This one you guys have seen often enough, and obviously D is our option there. Now, 1.8, it says the 3 resistors in the circuit diagram shown below are identical. Fine. It says if the reading on the ammeter A1 is I, what will be the reading on ammeter A2? Okay, important. Here they say that they are identical, guys. They tell us that they are identical. So now we need to go and use this information. So they tell us that here, this current in A1 is I. I don't know what is this here. So it's kind of like this, right? So let's say, for example, this was probably the best number to work with here is probably going to be 3. So let's say if we have this as 3 ohms, 3 ohms, 3 ohms. So basically we have a situation like this, where we have our top branch, which has 3 ohms, 3 ohms. So obviously the top branch is 6 ohms. Bottom branch is just going to be 3 ohms. They tell us the current here is a certain value, right? They tell us the current here is some value. Now let's actually put a value to it. So let's say the value is, normally we just say 1. We say the value is 1 amp, right? So the value is 1 amp going through the top, because you know it's going to split there, go to the top, go to the bottom, rejoin, and then flow as total all the way, so that we can get to our A2 value here, or A2 ammeter, I should say. Okay, so to do this quick and easy, all we're going to do is we're going to say, okay, the voltage for the top branch, the voltage for our top branch is going to be what? So simple. Our voltage for our top branch is just going to be I times R. So our current is 1, our resistance is 6, so it's just going to be 1 times 6, so that's 6 volts. Right, so we know that this is 6 volts. That means for sure we're going to have 6 volts in the bottom branch, and then our current in the bottom branch is just going to be 6 divided by that, so that's 2 amps. So now we should definitely know what our actual total current is going to be. The total current here is going to be 3 amps. So what we're saying is that if this is I amps, this would actually be 2 I amps, because it's going to be double. And then the total current in A2 is going to just be 3I. So option A is B. Any questions, guys? Please let me know, yeah? All right, 1.9. It says in the diagram below, a straight current carrying conductor Z lies between 2 magnets X and Y. The conductor experiences a downward force when placed between 2 magnets. Okay, so first up, we need to understand that here it's a little bit of our knowledge on electromagnetism that needs to come through. All right, so here it says the direction of this here is downwards. So here it's like the thrust or your thumb that is going downwards. Okay, so let me give you guys a moment to just think about it using your hands and decide whether it's the left hand or right hand and see what you guys come up with, eh? Okay, let me just let you guys know now immediately also. It says a straight current carrying conductor Z lies between the two magnets X and Y. So we're saying that the current is not being induced here, right? We're not creating the current. The current is already coming through, which means that this must be a motor, right? So this must be a motor. Now, if we're dealing with it as a motor, guys, we were supposed to know that motors are the left-hand rule. Okay? Motors are the left-hand rule. So here, all I need you to do is use your left hand, and you guys know it must be perpendicular. We know that our thumb must be facing downwards. Our thumb should be facing downwards. So have your thumb face downwards. Okay. Now, if your thumb is facing downwards here, guys, what we'll notice, right, is that now you see lines between two conductor experiences, downward force and placement. Okay, yeah. So what we're going to see here is that then most likely what's happening is that our field lines, our forefinger, our index finger, is pointing in that direction. So our field lines are going in that direction, right? So thumb is down and forefinger is pointing this way, which means our middle finger should be pointing into the page. Our middle finger should be pointing into the page. So here we're looking at field lines going X to Y, and we're looking at our current going into our page. Current going into the page. Let's see if that's an option. So X to Y, yes. Perpendicular. Oh, into the page. Yeah, perpendicular and obviously into the page. Yeah. So option A is our option here, guys. Okay. 1.10, it says the graph below shows the relationship between kinetic energy of the ejected photoelectrons and the frequency of the incident radiation. Fine. Here it says which one of the following set correctly shows the information provided by P, Q, R, and S. Okay. So firstly, immediately what we need to know is, and we've done this, the gradient of this graph is always going to be Planck's constant. So this will always be Planck's constant. So immediately we know it's not A and we know it's not D because, yeah, it's not A and it's not D because there it says that it's threshold and work function. So it's not A and D. Let's see the next part. Q represents FO. Q represents threshold frequency. Yes, it does. So option there is C. We know it's not B because it's definitely not the work function. Okay, done. Sorted out. All right, guys, let's get into our question 2 and go from there. Guys, please, if there's anything from the multiple choice that you want me to go through again, let me know, yeah? So here they tell us that two blocks, A of mass 15 and B of unknown mass M, are connected by a light inextensible string on a rough surface. Wonderful, we know it's a rough surface. A force of magnitude 120 newtons is applied to block A at an angle of 30 to the horizontal. Find the coefficient is 0.2 for both blocks. That's rare. Especially if it's of different masses, but it's fine. So 0.2, unless it's the same materials that we use. But anyway, 0.2 there is our coefficient. It says the system accelerates to the right at 2.08. So we know that we're actually moving in that direction. Acceleration is 2.08 meters per second squared. All right, now let's get into this here. Newton's second law of motion in words. Guys, Newton's second law of motion basically says that the net force acting on a body is directly proportional. Sorry, I should say that. Yeah, I should actually say that the net force acting on a body is directly proportional to the acceleration, and the acceleration is inversely proportional to the mass of the body. Okay. 2.1.2, draw a labeled three-body diagram to show all the forces acting on A. Good. But guys, we know this. We don't, as soon as we're dealing with two objects, we never draw one three-body diagram. If we're dealing with two objects, we draw two separate free body diagrams. Please get that out of the way, and that's going to sort out 2.1.3, guys. Okay, so I'm going to draw it here. Block B, block A. So block B, we don't know the mass. We know this one is 15. So this is the 15 kilogram. Okay, so what we should know from this is block B is just being pulled along with block A. So that's just a tension, and there's going to be a frictional force acting backwards. Here, it's going to have a normal force up and a gravitational force down. For B is now where it gets a little bit more interesting. Sorry, not for B, sorry, for A it gets a little bit more interesting. We know it's on a surface, so for sure we're going to have gravitational and normal. Right? We know it's on a surface, so obviously there's normal and gravitational. That's things that we're supposed to know. However, we should also know that the applied is at an angle here, and then we should know that there's tension back and friction going back. Okay, so tension back and friction going back. Let's just make that a bigger circle. So we know that that's an applied force. Did they give us a value for that applied? 120. At an angle of 30. At an angle of 30. And we know now that this is going to be FAX and FAY. Guys, please, however, in your final paper, make sure you write out these words in full, please, because it must be written in full. So you can't write it here unless you put a key to it, right? So if you're going to put a key to it, that's also fine. But if you want to write out the full words, that's also fine. Okay, so there's our free body diagram for both. Obviously, we didn't have to. We just needed to draw it for A. Okay, then it says that we need to show that the frictional force experienced by block A while accelerating is 17.4 newtons. Okay, so this is actually pretty simple, right? So they want us to prove that the frictional force on A is 17.4. Now remember, for A, they've actually told us that our coefficient of kinetic friction is 0.2. Right, so if they told us that the coefficient of kinetic friction is 0.2, for us to calculate the actual friction, it's actually really simple. It's a two-step thing. We first need to find out what is the normal force, and then after that we can find the friction. So how do we find the normal force? The forces going up must be equal to the forces going down. So don't forget that. Yep, the normal force plus the FAY should be equal to the FG. The normal force should be equal to the FAY, which is 120 sine 30. And then this should be 15 times 9.8. And then we get our normal force from there. And that's 87. And force of friction is equal to mu k times the normal. And that's 0.2 times the 87. And 17.4 exactly, guys. So there's our friction there, 17.4. Not the worst thing in the world. Okay, now let's take this to then calculate tension. And we don't need to calculate acceleration, just the tension. So 2.1.4, calculate the tension force in the string between block A and B. So we just want the tension force, guys. So with this information, so this, sorry guys, is 2.1.4. So 2.1.4, they want us to calculate what is this tension force here. So what I would suggest, we work first with block A, because here we have, unfortunately we don't have the friction on this side. So let's work with the things that we do know, right? Let's work with the things that we do know. So we pretty much have everything in this one here except the tension. Right? And in this one, we don't have tension, nor do we have friction. Right? But you could have solved it for like either way, but let's sort this one out. First up here, this is what we're going to do, is we are going to say that our F net for A, that direction is positive, is going to be equal to FAX minus the tension minus the friction. And here we're going to say that this is a mass of 15 times an acceleration of 2.08. 2.08 there. Okay, so here, 2.08 FAX is what we're going to be sorting out now. So this is going to be 120 cos 30 minus tension minus the friction of 17.4. And now we just solve for tension, guys. Okay, so 55.32 newtons, guys. That's our tension, 55.32 newtons. Guys, anyone with questions on this here, please let me know. Nope, seems to be good. Okay, I know this question is not asked here. I know that it's not asked here. However, what I would like for you guys to do is please calculate the mass of block M for me. Sorry, not block M. Calculate the mass of block B. Sorry about that. Calculate the mass of block B, guys. Let's see if anyone can do that. It's not a difficult question. I do hope that one of you guys would be able to sort this thing out. Okay, guys, what I'm hoping we are going to do is the following. Let me start this off and show you guys what I would hope for us to do. So this is 55.32. Now, what we're going to do now is we're going to say, okay, F net in that direction, positive, is equal to, here, it's going to be our tension minus our friction. This is going to be M times an acceleration of 2.08, if I'm not mistaken. Yeah, 2.08. Okay, small mistake with what we've done there. I'm going to explain. So, guys, here, let's see. Okay, guys, the two guys who sent me pictures of how they calculated it, you guys have made two silly mistakes. Let me just explain this. So the tension is going to be the 55.32. Now, minus the force of friction. Force of friction is mu k. So this is the mu k times the normal, right? And the normal force here would basically just be equal to the gravitational force there, right? So that's just going to be mass times 9.8, right? So here it's going to be 2.08 m is equal to 55.32. Remember here, guys, you can't do this. You can't do that separately like that. No, because this is already multiplication. So this is basically like this. This is 9.8 m already. So it's 0.2 times the 9.8. which is going to be 1.96. So it's 2.08 m, which is equal to 55.32 minus the 1.96 m. Let's just see here. Okay, so just, guys, I think we forgot. A few of you guys made like silly mistakes through the way, man. Guys, remember this is MA. Let's not forget about the acceleration. But like, I'm glad that like the main concepts of the tension minus the friction, you guys got the friction part, which was normally the worst part of remembering this year. But we made mistakes along the way. For those who sent me pictures, right? So this is going to be 2.08 plus the 1.96, which is going to be 4.04. So 4.04 here is equal to 55.32, and then I'll get my mass from there. So just going to take 55.32 divided by 4.04, and that's 13.69. 13.69 kilograms. Okay, guys, I hope this makes sense. Any questions that you guys have, let me know, yeah? Okay, guys, now 2.2, it says consider a satellite of mass 1,200 orbiting the Earth at a distance between the center of the satellite and the surface of the Earth is 36,000 kilometers. So the surface in there. Okay, so immediately I just want to go and get the radius of the Earth so that we know it and the mass of the Earth because we're going to need those values. Okay, mass of the Earth 5.98 times 10 to the 24. I'll just write that down, right? Times 10 to the 24. And then where's the radius? Radius is 6.38 times 10 to the 6. I just want to save those values on the calculator. Okay, so here, I'm just going to write it down here so we know it. Mass of the Earth is 5.98 times 10 to the 24 kilograms, and the radius of the Earth is 6.38 times 10 to the 6 meters. Okay, so it says state Newton's universal gravitational law in words. It says calculate the magnitude of the force that the Earth exerts on the satellite. So yeah, guys, it's a really simple one for us to do. I just want to normally just use that there, so we have some space here. Okay, so guys, yeah, normal force formula. I don't think we really need to go through this in much detail. You guys know this is Newton's universal, which means we must go from center to center. That's the way it works. So 6.67 times 10 to the minus 11. The first mass is the mass of the actual Earth, so it doesn't really matter. Actually, could have been the mass of the satellite, but 5.98 is what I'm going to go with. Times 10 to the 24. The mass of the satellite is 1,200 kilograms. It must always be in kilograms for your mass. Your distance must be in meters, however, right? Distance must be in meters. So the radius of the Earth is 6.38 times 10 to the 6 meters. We need to now convert this into meters as well. So that's going to be plus 36,000 times 10 to the power of 3 all squared, because we're going to convert it to meters. So here, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 1,200. 6.38 times 10 to the 6 plus 36,000 times 10 to the 3 squared, and that's 266.49 newtons. So that's the force that the satellite exerts on Earth, the gravitational force that the satellite exerts on Earth, and what Earth exerts on the satellite. Okay. Also, let me check. Okay, yeah. Okay, so the question is, when do you use this G formula here? You use this G formula here typically when you are dealing with like some sort of celestial body where this represents the mass of the planet and this typically represents the radius of that planet. So all you're going to be doing here is maybe they give you the gravitational acceleration, or they want you to calculate the gravitational acceleration on this planet. They give you the mass of the planet, they give you the radius of it, and now you calculate the gravitational acceleration, right? Or they can say, okay, we need to calculate what would we weigh on this particular planet, and it's a similar situation. You get the gravity and you just times it by the mass if you want to do it like that. So it's more relating to like one particular celestial being, to calculate what gravitational acceleration would it actually exert on its surface. That's what this formula is normally used for, just to find what gravitational acceleration would it exert on its surface. Okay, 2.2.3, how will the force that the satellite exerts on the Earth compare to the answer in that there? Obviously, if it's on the Earth, we're expecting it to be greater than. That's just an obvious thing. We know that because it's going to be closer. The closer we are, the stronger the gravitational pull. Right? That's just very, very obvious. Just want to make sure that I did this, I read this properly also. How will the force that the satellite exerts on compared to the... Oh, sorry. Did I? Did I? Did I do this wrong? No, I just did the English sometimes in these questions. How will the force that the satellite exerts on the Earth compared? Oh, no, 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 no. That's my bad. That's my bad. It's what the Earth exerts on the satellite, and here it's asking us for what the satellite exerts on the Earth. It was what I was explaining earlier, that whatever gravitational force that the satellite exerts on Earth would be the same that the Earth exerts on the satellite. So for this one, it should have actually been, should have been equal to, because they exert the same gravitational force on each other. Sorry about that, guys. Okay, question 3. It says that a hard plastic toy, 0.6 meters high from the ground, is placed next to a block of flats. A child leans over the edge of the roof of a building 21 meters above the roof of the car. It says the child throws a tennis ball with a mass of 73 grams vertically upwards. So immediately convert the mass to kilograms. So 73 times 10 to the minus 3. Okay, it says the tennis ball moves upwards to point X, falls back past the top of the building, hits the roof of the car after 3.77 seconds. After, sorry, ignore all the effects of air resistance, takes upward motion as positive, fine. Okay, so it's thrown upwards, right. So it says here, is the tennis ball, while moving downwards towards the car, in free fall? Write down yes or no. Yes, it is still in free fall because there's only gravity acting on it. So obviously it's still going to be in free fall. As long as gravity is the only thing acting on it, it's going to be in free fall, guys. As long as gravity is the only thing acting on it. Okay? Then we go on to 3.2. It says here, the magnitude of the velocity with which the tennis ball was thrown upwards. Simple. So here we just want to know what is the velocity at which the ball was thrown upwards. Now the important thing here is they tell us, it says it falls back past the top of the building and hits the roof of the car after 3.77 seconds. So they're telling us that this entire journey here took 3.77 seconds. That's what they're telling us. So we want to find out what is the initial velocity that it was thrown up with. So we're going to find out what is that velocity there. Actually, not the most difficult thing in the world. Because now we can use our formula, delta y is equal to vi delta t plus a half g delta t squared. Now, I just want to find out from you guys, if we are taking up as positive, and that's what they wanted us to do, taking up as positive, what would our displacement be for this motion until it hits the top of the car? Guys, what would our displacement be until it hits the top of the car there? Apologies. Sorry, guys. Okay, so now that exactly that minus 21 meters is perfect because our displacement from start to end, our displacement is always going to be the shortest distance from start to end, but it's going to end up being going down, so that means it's minus 21. So this should be minus 21 meters. Our time is 3.77. We know that gravity should be a negative 9.8, guys, and that's 3.77 squared. And then we just solving for our initial velocity. Okay, so I'm getting it as 12.9 meters per second, guys. I'm getting initial velocity as 12.9 meters per second. Yeah. Okay, so the question is, if we take up as positive and we actually end up moving downwards, our displacement is negative, and why is that? It's like this here. So let's think of it on a horizontal plane first, and then we'll go to the vertical plane. So let's say I told you that we moved this way. So we're taking that direction as positive, and then we moved back this way. So we went 20 meters that way, and then we went 30 meters this way. Right? So now if we're saying that, then what we can do is we can say that, okay, here to here is our displacement. From start to end is my displacement. So my displacement in this case would actually be minus 10 meters, isn't it? Because I took that direction as positive. Now in the exact same sense, right? Let's do it this way here. Let's say that I'm going up, but then I'm actually coming back down like vertical projectile. So we're going to say that this distance here is 50, right? This distance here is 20. But now I want to know what is my actual displacement for the entire motion of this. So my entire motion of this is going to be what? My displacement is always going to be the shortest distance from start to end. So obviously my shortest distance from start to end would be that 50, but it would be a negative 50 meters. Hope that makes sense. Okay, so it's a really easy concept, guys. A really easy concept. See if I have any more questions. Can we use a formula with VF equal to 0? Okay, so question is, can we use a formula with VF? So can we do this? Can we say that VF here is 0 at the top here and then work from there? It's a bit difficult to do that because we don't know what the velocity is at the bottom here. We don't know what the velocity is at the bottom here. So we can't really find out a time value for us to work backwards. So probably the only way to do this one is actually to get that initial velocity like this with this formula. Okay, guys, 3.2.2, maximum height that the tennis ball will reach above the ground. Okay, so all we need to do is we now need to go and calculate this maximum height that will reach above the ground. Okay, take a moment and let's sort that out, guys. Okay, there's 3.2.2. Just do it. Yeah. So 3.2.2, we know we want to find maximum height, so we can just say that, okay, VF squared is equal to VI squared plus 2G delta Y. The VF at the top is 0, we know that. So that's 0 squared. Initial we now know is 12.9 squared. Know that this is 12.9 now. And that's going to be 2, and if you're taking up as positive, this is minus 9.8 delta y. So once we solve for delta y here, guys, it's 8.49 is what I'm getting it here. Okay, so 8.49. But the total height above the ground, is the important. This is the total height above the ground. Is that plus the 0.6 plus that there, plus the actual height that we got here of 8.49. Right, so it must be the summation of all of those there, guys. So total height above the ground would be 8.49 plus the 21 plus the 0.6, which is going to be how much? 30.09. So 30.09 meters, and we're done. Okay. So let's just put that as our total height here. 30.09 meters. Okay. Now what it says is that the tennis ball strikes the roof of the parked car with a speed of 24.04 meters per second. So now they tell us a little bit more information. They say that, okay, our velocity when we hit this particular car, the velocity when we hit that particular car, actually, let me just still keep that there because we'll need it eventually again. I'll just take this piece away here for this window so I can write it out here. So the velocity at which we hit the car is 24.04. So 24.04 meters per second is the velocity at which we strike the car. Okay. It then says that we need to assume that the roof does not get dented. The tennis ball bounces inelastically on the roof where the rebound speed of the tennis ball is 25% lower than the speed at which the tennis ball strikes the roof of the car. Okay, if it's 25% lower, it's basically telling us that it's only 75% of what it was. So if you want to find out the velocity at which this is actually going to go back up at you, because you remember that it's going to strike the top of that roof, and it still has to do this. It still has to go up and then come back down, right? It still has to go up and come back down. So let's put this in this darker green. So this second motion here, guys, what is the velocity that it's going to be going up at? So I'll put it here. I'll say that the velocity that it's actually going to be going back up at is going to be 24.04 times 75%. So 24.04 times 75%, 18.03. So 18.03 meters per second is the velocity at which it's going back up. It says the tennis ball is in contact with the roof for 0.1 seconds. So it's in contact with the roof for 0.1 seconds. Calculate, oh, okay, impulse. Okay, so let me just redraw the situation here because it'll be easier for us to understand. 3.3. Okay, so 3.3, the scenario that we have is roof of the car. We're basically striking the roof of the car at 24.04 meters per second. We're going back up at 18.03 meters per second. The mass of the actual object that is striking and then bouncing back up, the mass of that is 73 times 10 to the minus 3 kilograms. They told us 73 grams in the beginning, and then we converted it. Okay, so now if they want to calculate impulse, guys, impulse is really easy for us. We would know that impulse is basically the change in momentum. So here, impulse is just going to be equal to mass into final velocity minus initial velocity. Mass is 73 times 10 to the minus 3. Final velocity, we need to choose a direction as positive, right? So we just can, let's see if I choose going down as positive. The final velocity would be a minus 18.03 minus the 24.04, and then that's our answer. Okay, so here we're getting this as minus 3.07, and this is normally measured in Newton seconds. So if they just want a value, so it's 3.0, I'm sure they just want the magnitude value. Oh no, they don't actually ask. So impulse itself. So we're going to say that even though we chose down, this is actually 3.07 Newton seconds acting upwards. Okay, sorted out. Any questions on this here, guys? Okay, guys, done there. 3.4. It says sketch a velocity versus time graph for the motion of the tennis ball from the instant it is thrown vertically upwards until it bounces off the roof of the car and reaches its highest point. So they want a scenario for this here. They basically want this. when it's thrown off the roof till it hits the car and then reaches its new maximum height there. That's basically what it wants for the velocity time graph, just so we understand. You should know that that's the car there, essentially. All right, so it says indicate the following on the time taken to reach the roof of the car, the time at which, okay, so let's go and explain all of this here. I think for me to do that, it's best for me to do it on the side here. So I'm just going to take all of this away and then just draw it on this side. Let's just shift this whole thing. Okay, so let's use this side of the page to draw the velocity time graph. Right, so let me put it a bit straighter. Wow. Okay, so things that we were supposed to know. First up, we started at 12.9 meters per second. So we say, okay, positive, because we're taking up as positive, so that's 12.9. Remember, this is the velocity time graph. So basically, we don't know how long it takes for us to get to the maximum height, because that's the maximum height there where our velocity is 0. But we know that for us to go to this for us to go to this velocity of 24.04, it takes 3.77 seconds. So for us to go to a velocity of 24.04, which is basically a negative 24.04, it takes us a total of 3.77 seconds. And then what they tell us is we obviously bounce back up. We bounced back up at that 18.03. So we bounced back up at a velocity of 18. Obviously, I'll just put that there as 18.03 until we reach a maximum height again. Basically, they're talking about this motion here. Look at this building here, guys. They're looking at this motion here from here to the top, to that maximum height. And we know at maximum height, our velocity is 0. What we need to remember is that these lines must be parallel to each other. Done. So that's what our velocity time graph would look like. Okay, questions? Anything that you guys want to ask? Now's the time. Like I said, this was a really nice type of paper. I was wondering why I didn't see it before, but yeah, I just thought it was such a nice paper. Okay, guys, question 4. Let's get into this here. It says a metal sphere of mass m is suspended from a chain at a height of h above the ground at position A. The sphere is held in position A by means of an electromagnet as shown in the sketch below. When the electromagnet is switched off, the sphere swings down and moves past position B. Okay, fine. It says the lowest position of the trajectory is 2 meters per second, striking the stationary crate X of 2 kilograms as a mass. Ignore all friction forces, right? So everything, there's no friction, right? No friction at all. So no friction while it's air friction. There's no friction here, on the ground here, nothing. So what they tell us for this point here, we need to know this here. Here, we're basically just releasing it. So there's no kinetic energy. The velocity here is 0. So the kinetic energy is also 0 here. Okay, it says the potential energy versus kinetic energy, EK, graph below represents the motion of the metal sphere from position A to position B. The angle of inclination of the graph is 135 as shown in the, as shown below. Okay, so they basically just want us to find out, or they want us to figure out, why is it that here we start off with potential energy, right, at its maximum. Why do we start off here with potential energy at its maximum? And then eventually, all that potential energy is now going to be converted. I should write it like this. All that potential energy is now going to be converted into kinetic energy. Now, let's have a look at our diagram here. That potential energy, we start off with it being right there. We know that there's 0 kinetic energy, like we said at the start. As this moves further and further down, it starts to have kinetic energy, starts to have a velocity. And that velocity starts to increase all the way down to the lowest point, and then it slows down again. So here, guys, we know the following. We know that at this point, EK3 is basically position B. This is basically position B. This is basically position A. That's what we need to understand. 4.1, it says show that the gradient of the graph can be this here, where G is the gravitational. Okay, so here they just want you to prove that that's what the gradient can be. So gradient in this case here is going to be what? Change in potential. Sorry, it's basically change in EP all over the change in EK. Right? So all we're going to do from here is we'll say you can choose 2 points. You can choose 2 points here. It doesn't really matter which 2 points you choose. It really doesn't matter. So here it's basically mass times gravity, and then there'll be a change in height. So height final minus height initial. Here it's a half of your velocity final minus your velocity initial. Now, like we discussed earlier, we said that this height, the initial height is the biggest height. The final height is actually 0 here. The final height, which is here at the bottom, is actually 0. So this gets cancelled out. Here for the velocity part, the final velocity for where it's moving here is the greatest. So here we actually have a final velocity, but the initial velocity we start off with is 0. So that kind of goes away. So what we're left with here is hg minus hi all over a half into minus, and that should be, obviously, sorry guys, that should be squared. Each one should be squared, sorry. Each one there should be squared and squared. Squared. And yeah, so when we do this, sorry, VI, sorry, that's VF, apologies. That should have been VF squared. A half of your mass times your VF squared. Okay. Now all we're going to do from here is we're going to have this as negative mgh all over a half mv squared, and you know from there your masses can cancel out, and once your masses cancel out you just have this as negative gh all over a half v squared. Okay, done. Right, 4.2, it says, at which point on the graph is the mechanical energy of the metal sphere equal to the kinetic energy? Choose from EK1, 2, or 3. So they want to know when is the mechanical energy of the metal sphere equal to the kinetic energy? So they want to know basically when is mechanical energy equal to kinetic energy? The only time mechanical energy can equal to kinetic energy is if the potential energy is 0. So where do we have the potential energy as 0? Obviously the only place where the potential energy is 0 is EK3. EK3. All right. 4.3 says use information on the graph and show that the height h from which this metal sphere is released is 0.2 meters. Okay. Does it give us anything else here? 2 kilograms, 2 meters per second. Oh, okay, yeah. So basically for, what is this, 4.3. So for 4.3, all we have to do is we need to say that EP at the top should be equal to EK at the bottom. Potential energy at the top should be equal to the kinetic energy at the bottom. So yeah, because there's no potential energy, and there on the top there's no kinetic energy. So here it's just going to be your mass of 2 kilograms times 9.8 times our height that we need to calculate. EK at the bottom is basically a half times 2 times the velocity squared of 2 squared there. Okay, and then we calculate the height. That's 4 divided by 6, and that's 0.2. Yeah, we're just going to go 0.2 meters. So this height is 0.2 meters. There's just a lot of number 2's here. Well, just lots of 2's. Okay, easy one that. Okay, there was a weird one. I think it comes after that. Yeah, okay. Yeah, it says question 5. Weird question. Question 4, it says, if the work done by the conservative force on the metal sphere is 19.6 joules, determine the mass m of the metal sphere by using energy principles. Wait, did I make a mistake here? I did. I did make a mistake here. Sherbet. This mass should have just been m. This here is mass m. This here is mass m. Eventually, they'll still cancel out, and the height would actually still be the 0.2 meters. So if they probably didn't want us to use that there. How else could we have? Okay, so guys, let's say they didn't want us to do it this way. Let's say they wanted us to use, because I see they wanted us to prove this. So normally when they want us to prove it, we have to use it at some point. Guys, the gradient of this particular graph, obviously the gradient, just using maths, the gradient of this graph would be -1, right? So the gradient of that graph would be -1. So we could actually use this gradient, because we know gradient is equal to that. So for 4.3, we could have actually done this, that the gradient of -1 is equal to negative gravity times the height, all over half times the velocity squared of 2. And then just go with it from there. So here, so I guess let me just see that two people have messaged. Yeah, sorry. Alia, thanks for that there. Where did the -1 come from? Oh, yeah, I should have explained. So guys, here, where did this gradient of -1 come from is because of the angle here. The angle here is 135. The angle here is 135. So what does that tell us, guys? What does that tell us? That tells us that tan of 135 is equal to the gradient, isn't it? Because that's the angle of inclination. So if you put tan of 135 in your calculator, it's going to give you a gradient of -1. Okay, guys, no one's asking anything there. It's an easy thing. All right, so from here, basically this is going to give us, that's basically just going to give us -2 is equal to -9.8h, and then it's 2 divided by 9.8, which is 0.2 here. So that's 0.2 meters. That's another way we could have done that. So, guys, which formula did I use? I used this formula where we prove that this gradient is equal to this minus GH. I should write this better. We prove that gradient is equal to this minus GH all over half V squared. That is equal to that there. Okay, guys, I hope that makes sense. Guys, any questions, please let me know. So I did like this paper, that's why I wanted to add some questions to it and explain things additionally, because it's really been like a different paper, that we haven't really done weirder questions like this. Okay, it says at the lowest point of its motion, the metal sphere collides with a stationary crate X, and that it's 2 kilograms. After the collision, the crate moves horizontally to the right with a speed of 0.3. Determine the velocity of the metal sphere immediately after the collision. Okay, now it basically just becomes momentum. Easy momentum. Okay, so what we would know from this situation, and I can just take this away now, we don't need that. Okay, so what we need to do now is we need to know the values. So we know that this particular, I don't like the way they've shown it as this is, I'm going to put it in green so we know it's specifically for the sphere. So I'm going to say that this is 2 meters per second, and that's for the sphere. The crate moves off at this 0.3 meters per second. The crate moves off at 0.3 meters per second. At 0.3 meters per second. We know that the sphere has a mass of 0.2 kilograms now. So now we're just going to say momentum before is equal to momentum after. So we're going to say that 0.2 times its initial velocity, which is here just before the collision. So that's 2 plus the mass of the crate. The crate is 2 kilograms. So 2 times its velocity just before the collision is 0. And then we have this as 0.2 mass of the sphere after the collision is Vf plus mass of the crate, which is 2 times its final velocity just after the collision is 0.3. We have that as 0.4. We have that as 0.2 Vf. We have that as 0.6, and we're calculating the final velocity there. Okay, so yep, guys, actually pretty simple for us to do. Oh my god, I did. Oh my god, I did. I'm wondering why we're gonna mess this up, because this is 0.2 m. Because we calculated the height to be freaking, the 2's are messing me up here. 0.2 meters, yeah. It's like that doesn't make sense in terms of what its value is going to be. So this should be 0.2, yeah, because it is h. So we could have actually kept it as h there, and h there, and h there, and then yeah, the thing is we should have actually said 0.2 m is equal to a height of 0.2. And then we said that no, sorry, that's right. The height is 0.2 meters. Where did we calculate the mass? I'm sorry, guys. I'm just losing myself here. Where did I calculate the mass? No. No, I didn't. I just skipped over that question. If the work done by the conservative force on the metal sphere is 19.6 joules, determine the mass m on the metal sphere by using energy principles. That is so bad of me, guys. Okay, the work by the non-conservative force on the metal sphere is 19.6 joules. Determine the mass of it by using energy principles. So the work done by non-conservative force on this swing. Guys, I need you to know this here. Let me just redraw this. I'm so sorry about these mistakes, man. Such a silly mistake. So for this object that is 0.2 meters above the ground, we actually don't know the mass still. On its swing downwards, guys, does anyone know? Because, okay, they told us that there's no actual friction. What do you think the non-conservative force is going to be here? Please note that the non-conservative force here is going to be the force of gravity, right? So basically, the work done by gravity is a non-conservative. Yep. Sorry, not non-conservative, by conservative force of action is a conservative. I want to explain. This is a conservative force. Now, what makes something a non-conservative force? So a non-conservative force would be something like this. So we know that a non-conservative force is, for example, friction. But what we tend to also forget as a non-conservative force is tension, right? So if we had to take into account this tension on this rope, this tension would be our non-conservative. Right? Because it, yeah, the friction, the tension, yep, they all like, remember the definition that we deal with for conservative and non-conservative. Maybe if I explain the definition, maybe it will make a little bit more sense. So a conservative force, definition, I'm sure you guys have seen this, like the way it's with regards to the path taken, the direction of the path taken. Please note that a conservative force is independent of path taken. Now, why does it make sense that work of gravity is independent? Because you could be, it doesn't matter where you are, work of gravity will still exist. It does not depend on the direction you are going or anything like that, right? It does not depend on the direction between between 2 points. Gravity will still act going down. So gravity like that, going down all the time. Gravity like this here on an inclined plane, going down all the time. So it's independent of its direction. Gravity, if it's on a surface like this, is still going down all the time. So that's why we're saying it's independent of the path that's taken. Now, for a non-conservative force, a non-conservative force depends. It is dependent on the path taken. So if it is dependent on the path taken, it means that, okay, for example, for friction, if we are moving in that direction, friction goes this way. If we are, for example, if we are going in that direction there, friction must go in the opposite. So that's telling us that it depends on the path taken. Same goes with tension. Depending on which direction you go, tension will change. So for example, if these blocks, let's say this tension was going that way, for this block, tension is going the other way. You know, it's dependent on the path taken. Here, it does not depend on the path taken. Like, just so that you can understand where the definition comes from, because before we would just write down the definition, and I didn't actually fully explain it, and I apologize for that. But here, now we needed to know it. So here, conservative force, done. So what we need to know is that the work done by this gravity is 19.6 is what they tell us here. 19.6 or 9, yeah, 19.6. It's 19.6 there. So if that's the work done by gravity, basically the only work that gravity does is potential energy, right? The only work that gravity does is basically like its potential energy. So all we're going to do here is we are going to say, sorry guys, let's see if I have a question here. No, sorry guys, I thought I had a question. Okay, so for this, all we need to say is for the potential energy itself, work of gravity is basically the mgh, which is equal to the 19.6, because the only work that gravity does is because of its height above the ground. So here, the mass is what we're looking for, the 9.8 we have, the height is the 0.2 meters, and this is going to be the 19.6, and then we're going to solve for it from there. So that's 1.96, that's 19.6, that's 19.6 over 1.96, which is 10. Okay, so that should give us 10 kilograms. Okay, so the mass should actually be 10 kilograms. I'm so sorry that I just, you know what happened was, I read this 0.2 m as, oh, it's the mass is 0.2 m instead of the distance as 0.2 m, and I'm so sorry about that. Okay, so here we know that that's our mass is 10 kilograms. Now, all of this actually gets done a little better. So here, this is 10 kilograms for the sphere. So here we can say that this is 10 kilograms. Here we can say that this here is 10 kilograms. And then we just go and solve for it from there. Okay, so calculating this, I'm going to have that there as 20, and this here is 10 here, is it 10? Okay, yeah, done. So that's going to be 20 minus 0.6, 2.4 divided by 10 is 1.94 meters per second. Okay, just to run through it again. This is the velocity of, sorry, this is the mass of the sphere. Then this is the mass of the crate. Mass of the sphere, mass of the crate. Okay, so question 5. This was, when I read it, it was a really, really good question. I'm hoping it lives up to it. So it says Carla wants to investigate the relationship between work done by the net force and the kinetic energy on her. She slides down a rough inclined plane from rest using different masses of trolleys as shown in the diagram below. The unknown mass of Carla is m. So we know now that we don't actually have a mass. It says she performs this investigation using trolleys of different masses and records the results as shown in the table below. And this is what we have. We have the number of different experiments or trials, trial 1, 2, 3, and then the net forces, guys. So here we basically have we have 3 different net forces because it's 3 different, like, yeah, you see that it's masses of trolleys, three different, like, versions of them. All right, then it says that here's our change in our v squared. Now, guys, please note that as she slides down this particular ramp, things that we were supposed to know, okay, as she slides down the ramp, obviously, whatever velocity she started with here, whatever it was, we don't know what it was, this velocity at the end here should obviously be greater than that velocity that she starts with, because she's sliding down, right? Because she's sliding down. Unless it's like, unless there's, for example, there's constant velocity. But guys, obviously, what we should know is that because we have net force values, because we have a net force value, we should have some sort of acceleration going downwards. We should have some sort of acceleration going downwards. Okay, now let's get into this here. So here it says that the number of trials is, okay, sorry, not the number of trials. It says that which one of the trials shows an incorrect, sorry, which one of the trials shows an, I'm guessing it should have been an incorrect reading, or which one of the trials is incorrect. I'm not sure what they wanted, but give a reason for your answer. So which one of these trials is probably going to be nonsense is what we're getting at here. So the trial that would probably be nonsense is this second trial here, because we can't have a change in velocity. So what they're saying in that second trial is they telling us that the velocity, the change in velocity here, this velocity final should be equal to this velocity initial, which means it should have been constant velocity. So they're saying here it's supposed to have been constant velocity, which, as we know, is definitely not true, because we actually have a net force. Okay, done. So we know that trial 2 is wrong, because delta v squared should not be 0. Delta v squared should not be 0. Five point two, use an appropriate equation to describe the relationship between net force and delta v squared. Now this was actually a cool thing. So when I read this, I was like, this is rare that they asked this. So how do you bring about net force and your change in velocity squared? It actually takes us back to work net is equal to change in kinetic energy. So work net, we know, is F net times a certain displacement. We know that EK is basically a half m Vf squared minus Vi squared, which is basically delta V squared. Delta V squared is basically your Vf squared minus your Vi squared. So now all we have to do from here is we've got to just make that subject of formula, and we are done. So what is our relationship between net force and this? Well, we can clearly see that net force is directly proportionate to the change in velocity squared. So they're directly proportionate. As our change in velocity squared increases, so does our net force. As our change in velocity decreases, our net force should also decrease. Now, let's see if that actually holds true in these two experiments that actually work. We know that this trial 2 is nonsense. So let's have a look at this. 5.76 versus 13.69. We see that the larger value, which is 13.69, produces a greater net force, makes sense. And then the smaller net force produces a smaller delta V squared. So it actually holds true for what we explained about proportionality. Done. Any questions there, guys? Such a good question, this. Okay, now 5.3. There's 5.3 says state the work energy theorem. We know that work energy theorem says that the net work done on an object is equal to change in the object's kinetic energy, right? Net work done on an object is equal to the change in that object's kinetic energy. Okay, so now 5.4, what does it say? It says use energy principles to calculate the mass m of Carla. Oh my God. Wow. Okay, so, okay, guys, for this one, let me explain. We're going to have to use these values basically to sort out an equation for ourselves. Okay, so we know this. This is what we know, right? This part here is what we know. So I'm going to actually sort that out in 2 steps here. So this is what is this? 5 point. I wonder if I'll have enough space to do it here. Let me try it. So I'm going to do this for trial 1 on this side, and I'm going to do it for trial 2 on this side here. Okay, so what we're supposed to know for trial 1, we know that it's F net times the delta X is equal to that a half M times the delta V squared. The same goes here. Yes, this was incredible, man. Okay, so here, guys, your F net for trial 1 is the 169, is the 169.41. You'll see it on the top there, 169.41 times the delta X. This is a half of the mass. The delta V squared is 5.76 squared. This is 442.91 times the delta X is equal to a half of your mass times this one, which is, oh, actually, not squared. That's already squared. So it's just 5.76. That's 13.69. So the reason why I'm not squaring it, guys, is because delta V squared is that actual value. See, delta V squared is the 5.76. Delta V squared is the 13.69. Okay. Wow. Now we actually have a simultaneous equation on our hands, and that's how we're going to be treating this, as a simple simultaneous equation. So honestly, it just depends on how you want to sort this out. Let's just make delta X subject to formula. Delta X here is going to be equal to, also the masses here, I should actually not make that mistake. The masses here, sorry guys, shit. Masses here, this is the mass of the trolley. The mass of the trolley is 30, and here the mass of the trolley is 40. So we should actually, because we want the mass of her, so for the first one, it's mass of 30 plus that 5.76, and here it's the mass of her plus 40 times the 13.69. So now we just have to go and solve for this. I'm just going to make delta X subject to formula on both sides. And this is 169.41. Delta X on this side, it's going to be our half into M plus 40 to 13.69 all over 442.91. Okay, so now all we're going to do is we're going to go and solve for this thing. So guys, I'm just going to take this over, and we're going to go and solve for the masses. hopefully this is going to be enough space here. Okay, so it's basically a half m plus the t into 5.76 all over 169.41 is equal to a half into m plus 40 into 13.69 all over 442.91. Okay, so that's that there. All we're going to do from here is we're just going to cross multiply and we're going to go and solve for it. So, guys, you guys can sort that out. Immediately, you can just divide both sides by a half because you can get rid of it that way, and then we can work with it from there. Okay, so mass that I'm getting, calculated, 69.7 kilograms. If you're getting like 69.8 or 69.6 something, it's fine. It's small rounding off, so it's okay. Okay, so 69.7 kilograms is what I'm getting as the mass of Carla. Okay, guys, let me know if you want me to run through this experiment thing again, and then we can go through it, yeah? I didn't even realize 5.4 was going to be this intense. Yeah, different. Very different. Okay, question 6. Let's see. So Doppler effect is applicable both to sound and light. Okay, done. Observer. Okay, so here it says that an observer at rest near the tunnel entrance can use Doppler effect to detect the speed of an ambulance. The ambulance approaches a tunnel in a mountain at a constant velocity. A stationary observer hears and detects the frequency of a moving ambulance as 1204.16, which is 1.0625 times the actual frequency of the sound emitted by the ambulance. Take the speed of sound in air to be that. Okay, so this is actually really simple. We're saying that frequency of the listener is 1204.16, and frequency of the listener is basically 1.0625 times the frequency of the source. So here we can also say 1204.16 divided by the 1.0625 is frequency of the source. So now we actually have the frequency of the source as well now. So 113. So 113.32. That's odd. That's odd though. Because is it approaching him? The ambulance approaches the tunnel. So he hears that amount. And that is no, mistake in terms of where I did that. Sorry. So this should be this here. It should be, I wrote that wrong. Okay, so because they told us here that the ambulance is approaching, we're expecting the source to be greater. We're expecting the source to be, to be less. We want the source to be less. Was it actually less? No, sorry, I did do it right. Sure, my maths was bad there. My maths was bad. 1, 1. Yeah. Yeah, I thought, I looked at this as 1, 3. And sorry, not 1,100. Apologies. Okay, so that's 1,133 for the frequency. Let's go back there. So we actually know we're fine with that, and we're fine with that. Sure. All right, so now it says 6.2, calculate the speed at which the ambulance approaches the stationary observer near the entrance of the tunnel. Okay, so for us to do this, all we have to do is we have to say that frequency of the listener is equal to V plus minus frequency, sorry, velocity of the listener plus minus velocity of source times frequency of source. So frequency of our listener is the 1204.16. Velocity of the actual ambulance is what we need to calculate. So we know that they told us to take this to be 340, which is the velocity of sound in air, to be 340. The listener is not moving, so that just stays there. The source is approaching, so this must become a negative at the bottom. So this is going to be 340 minus the velocity of the source, which is what we want to calculate, times the 1133.32. Okay. Oh, and yeah. Okay. So all we're going to do from now is we're just going to solve for velocity here. So it's 1204.16 times the 340 minus the Vs is equal to 340 all over the 1133.32. And yeah, we're just solving for that velocity of the source then, guys. Okay. Let's go and solve for this. 1, 2, oh, divide it on that side. So all I'm going to do, guys, here is I'm basically just going to divide it on this side. And then I'm basically just going to subtract the 340. So 340. Sorry, I don't know why I put that at the bottom. 340 into 1133.32. 340 times 1133.32 over 1204.16. That's 340. That's 20. Okay, so we're getting that as basically a flat 20. So velocity of the source is 20 meters per second. Yeah. I'll definitely explain that again. Yeah. So now we kind of had the same thought process there, and so I saw the number wrong. So I just want to explain why is this source less than this here? Well, because we know that if we are, remember, whatever frequency is heard, because we're approaching must be greater than the frequency of the source. That's why the source being 1133 is the source, and the frequency that is heard by the listener is 1200. So 1100 is the source, 1200 is what we actually hear. So that's why it's actually greater, and it makes sense that the frequency of the listener is greater. Okay, perfect. Okay, now 6.3, it says explain why the measured frequency is higher than the frequency of the source. Okay, so basically we know this here. They want to know why is this measured frequency, which is this one here, why is this one greater than this 1101? So obviously when you're approaching, you need to know that the waves or the wave fronts, the waves of the wave fronts are compressed, so greater frequency. So yeah, the reason for this, guys, just take this down so you know it. So actually, let me write it down. So you guys know that as you are approaching something, this would be if you are stationary, it's all equally distant apart. But as you approach, these wave fronts basically become smaller. And this is telling us that we have a greater frequency because they're happening more often. So what you need to know is as you're approaching, the wave, waves are compressed which increases, which increases frequency. Or you can say decreases wavelength. Because this would normally be the wavelength, this would normally be the wavelength, this. And now these wavelengths are so much smaller now. Because the wavelength is like the distance between two waves, essentially, between two crests, between two consecutive troughs and things like that. So obviously, as the wavelength decreases, frequency increases. Okay, I'll just make sure you guys have that. No questions, no. All right, because 6.4 tells us how would the frequency of that detected by the station observer change if the speed calculated increases. So guys, if the speed increases, so basically the ambulance is approaching this guy faster, if the ambulance is approaching the observer faster, if we increase the speed, what happens is, now these waves are now going to be closer, even closer to each other, because now this is pretty much catching up each time. So here it would actually be even smaller for these wavelengths. So even smaller wavelength, even smaller, like each one of those would be like equidistant apart, but I mean, it's much smaller than this idea. So if the wavelengths decrease even more, then that means that the frequency should increase if we are traveling even faster. So here, if we're increasing the speed that we are approaching the observer, or that we are moving towards our observer, we should also know that we would be increasing the frequency heard by that observer or detected by that observer. Okay, question 7. I know that this part of the paper was not like too crazy. This part, question 7, 9, and 10 wasn't too intense. So at least not so bad. 2-point charges P and S are placed a distance of 0.1 meters apart. The charge on P is 1.5 nanocoulombs. S is minus 2 nanocoulombs. A third point charge R, unknown, positive charge, fine. So we know it's a positive charge though. It's placed 0.2 meters to the right of the point charge S, as shown in the diagram below. And here it says we need to, okay, states Coulomb's law. We know Coulomb's law. Draw the labeled free body diagram showing the electrostatic forces acting on R due to P and S. Now, guys, here we're basically dealing with the net force. When we're dealing with the net force, the net electrostatic force, when we're dealing with the net electrostatic force at a particular charge, we don't look at field lines. When we're dealing with net electric, or I should say the net electrostatic force, what we look at is push and pull, right? When you're dealing with net force in electrostatics, we deal with it with this R being pushed away or being pulled, right? So with regards to P and R, is P going to pull R towards it or push it away? Obviously, it's going to push it away. So R is going to be pushed away because of P. So this is the force of P on R. Okay, force of P on R. Now, what is going to happen between S and R? Negative and a positive charge means that we're actually going to be pulled this way here. So this is going to be the force of S on R. Done. So that's actually your free body diagram. This is basically your free body diagram. So here we're just going to have this as force P on R, force of S on R. Okay, good. See if there's any questions. Nope, nothing is yet. If there is, I'll come back to it, guys. Okay. 7.1.3, it says that calculate the magnitude of the charge on R if it experiences a net electrostatic force of 1.27 newtons to the left. Okay, so it's saying that it's basically the net force is to the left. So we must take to the left as positive. Okay, and here it says take right up. Now, how silly is that? Wow, that is just dumb. Okay, so they want us to take the right direction. See, now this is also ambiguous, because if they say the right direction, it could also mean the correct direction is positive. So that's weird. But anyway, we'll just say we'll take the right as positive. This is so dumb. But anyway. Okay, we're going to take to the right as positive, even though they said that this is going to the left for the F net. This is just them trying to be difficult here. F net, we're taking to the right as positive. It's going to be F of P on R minus F of S on R. And yep, this is going to be the F net is 1.27 times 10 to the minus 6, but because it's actually going to the left, it must be a negative. And now we just need to fold this in. So here we know this is 9 times 10 to the 9. The charge of P is 1.5 times 10 to the minus 9. The charge of R is still unknown. And the distance here from P to R is 0.3 meters. 0.3 meters, because 0.1, 0.2, so 0.3 meters total distance there. 0.3 meters there. Here, it's going to be 9 times 10 to the 9. This is going to be charge S is 2 times 10 to the minus 9. 10 to the minus 9. Charge R all over a distance of 0.2 squared. Now, for us to go and solve for this here, all we're going to have to do is the following. We're going to take out QR as a common factor, and then this whole question is done. So you can just say QR taken out as a common factor, and you can just put QR here. You don't have to put it on the top of that. Just QR is equal to 9 times 10 to the 9 times 1.5 times 10 to the minus 9 all over 0.3 squared minus 9 times 10 to the power of 9 times 2 times 10 to the power of negative 9 all over 0.2 squared. And then you get QR from there. So basically, you just take this whole thing, you get this answer, and then you just divide it on that side. Not times 10 to the 9. Okay, so we're getting it as 4.23. Okay, 4.23 coulombs. So sorry, 4.23 times 10 to the minus 9 coulombs. There's questions that you guys might have on this here, please let me know, yeah? This one wasn't too bad. Really not the worst one. It's just the direction, just really upsetting. But anyway, it's fine. We're done with it. Yeah, it says 7.2. Point P is 0.5 meters from a charged sphere A. The electric field strength at P is 3 times 10 to the 7 newtons coulombs. So basically the electric field directed towards A, refer to the diagram below. Okay, so here they're telling us that the electric field is this here and it's directed towards A. Now guys, you know that if the electric field is directed towards A, right, when field lines go towards a charge, it means that this must have been a negative charge. If field lines move towards a charge, it must have been a negative charge. So yes, 7.2.1, draw the electric field pattern due to the charge sphere A. Actually, very simple. So we know that it's a negative charge and field lines should just be going inwards, guys. So the draw it perpendicular actually. Okay, so there's it there. It then says calculate the magnitude of the charge on sphere A. Calculate the magnitude of the charge on sphere A. Really simple. We'll say that for 7.2.2, that E is equal to KQ all over R squared. The electric field is 3 times 10 to the 7. K is 9 times 10 to the 9. The charge is what we are looking for, and the distance is 0.5 squared. And now we're just going to go and solve for Q. So 3 times 10 to the 7 times 0.5 squared over the 9 times 10 to the 9. Okay, and here we're getting this as now 8.33 times 10 to the minus 4 coulombs. Yeah, it's 8.33 times 10 to the minus, just make sure I've got the right thing. I've done this one, 0.5 squared, and then take that answer and divide by 9 times 10 to the 9. Yeah, perfect. 8.33 times 10 to the minus 4. Done. Okay, guys, for 7.2.3, it says another charge sphere B having a charge of minus 1.6 times 10 to the minus 14 coulombs is now placed at 0.2 meters to the right of P. Okay, so to the right of P, and it is a distance of 0.2 meters away. It's charge B, and it's a charge, sorry, it's not a charge yet. They tell us that it has a charge of minus 1.6 times 10 times 10 to the minus 14 coulombs. That's odd. You know what, I think it should have been minus 1.6 times 10 to the minus 4, because this is not going to really, it's not going to affect it. So guys, I'm not sure what is done or in the errata for this, if there was an errata, but I would actually make this times 10 to the minus 4, because if minus 14 wouldn't actually really make any difference because of this charge being so much bigger than the other one. So I'm going to say that this is going to be minus 1.6 times 10 to the minus 4 instead of the minus 14, right? Okay. So all we're going to do here is I'm going to say that this is minus 1.6 times 10 to the minus 4 coulombs. This one is 8.33 times 10 to the minus 4 coulombs. Now we need to understand the direction of the field lines. We know that this one, E for QA, is going in that direction. But for another, remember this is a negative charge. For another negative charge, we must have the field line also going towards the charge. So the field line would be going towards B as well here. So B's field line would be going towards it. So we know that if we wanted to calculate the net electric field at point P, E net would essentially be equal to, you can choose whichever direction you want as positive. It really doesn't matter, whichever one you want. Let's say if we chose going to the right here, going to the left here as positive. If we chose going to the left here as positive. So this is going to be E for QA minus E for QB. We know that E for QA, they've given it to us as 3 times 10 to the 7 there. So this is 3 times 10 to the 7 minus 9 times 10 to the 9, because this is K, times the QB, which is 1.6 times 10 to the minus 4, all over the distance of 0.2 squared. And we get our E net from there. Okay, so minus 6 times 10 to the power of 6, so which is actually just going to be 6 times 10 to the power of 6, because they just wanted the magnitude. 6 times 10 to the power of 6 Newton per coulomb. Right, newtons per coulomb. Okay, guys, any questions that you guys have here, please let me know, yeah? So this one, again, not the worst like the other ones. The other ones were like just really new questions. Okay, question 8, guys. Here it says, grade 12 learners are conducting an experiment to determine the internal resistance of a battery. The learners are divided into 2 groups. Group 1, use battery 1 with an internal resistance of R1. Group 2, R2. This is just an obvious thing. Obviously, they're saying that they have 2 different internal resistance here. It says the results of each group are shown in the graph below. Okay, so what we noticed is that both of them have the same EMF. So the maximum voltage output here is 12. Right? So the maximum voltage output for both of these are 12. Okay. Here we have it as voltage over current. So that would be our gradient here. Just so we understand, just so we already know that our gradient here, let's actually write it on the side. Our gradient here would essentially be the change in voltage over the change in current, and we know that voltage over current is resistance. So we know that it's representing some sort of resistance. What resistance does this actually represent? This gradient, because it's constant, this gradient represents internal resistance. So this gradient doesn't just represent any resistance, this gradient specifically represents internal resistance, because it's constant. This gradient is constant for itself, and this gradient is constant for itself. Okay, so 8.1.1, explain why the voltmeter reading across the batteries decrease as the current increases. Okay, why would the voltmeter reading across the battery decrease as the current increases? This is going to just take you to a formula that you've seen before. So let me show you guys this formula here. EMF is equal to I into big R plus small r. So they saying, explain why the reading across the battery decreases as current increases. We can see here, as much as this here is going to remain constant, right? We know that we have a formula that says that potential difference at source should be equal to your current total times your resistance total in your external circuit. We also know here that as your current increases, the amount of voltage that is lost is also going to increase. So let me go and explain it like this. Okay, wait. Sorry, guys. Let me explain like this, because I don't think you've done this too often. So let me just break this up first, so I can explain this. Okay, let me explain it like this. Just because using this formula here would be a lot easier than for me explaining it like this. So first up, this is going to remain constant, right? So this part is constant. Now, remember, this would essentially represent your total voltage. This would be your potential difference at your source. That's what this piece would represent. PD at source. This would represent lost volts. Now, using that logic, if your current increases, the amount of lost volts that you have would also increase. So that's something you need to know. As current increases, lost volts also increase. Therefore, potential difference at source decreases. Because remember, for this to remain constant, if this goes up, then this one must go down. Hope that makes sense, guys. Guys, if you want me to re-explain that, let me know. Okay, yeah, let's go and re-explain that there. I'll just rewrite it again because I was going to do it the way that I used to explain it, but I think this way would be a better way because it's going to relate to this experiment. Okay, so let me just re-explain this here. EMF I into big R plus small r. So EMF is equal to IR plus I times small r. So I'll just go and explain where all of these formulas and where am I getting them from. So this EMF, remember EMF is always going to be constant, right? It's the maximum output of the battery in terms of voltage. This here, put it in the screen, this I times R is basically potential difference at source. This I times R comes from V total is equal to I total times R total. That's where that comes from, right? This IR comes from this formula here. You know that small r is equal to lost volts, which is EMF minus potential difference at source. I always told you guys that this here represents lost volts. EMF minus potential difference at source is lost volts. So basically, this is, let's put it as lost volts all over I. We know that it's EMF minus the potential difference at source, right? So here, division becomes multiplication. IR is equal to lost volts. That's our lost volts here. Now what we're saying is, if your current increases, your lost volts will also increase. If your current increases, your lost volts will also increase, which means that this should decrease. Because remember, that must remain constant. That must remain constant. If your current increases, your potential difference at your source must decrease so that your EMF can remain constant. I hope that makes sense, guys. Now, to bring it back to like baby physics, if your current increases, so I'm just follow it here. If your current increases, then that means that your resistance would decrease. Your total resistance in the external circuit would decrease. And we know that when total resistance in the external circuit decreases, we know that potential difference at source also decreases. But this is the why behind it. Before I would just explain it as this. I just say, okay, as current increases, total resistance obviously decreases, and then that means potential difference at the source would also decrease. But now I'm explaining to you as the why. Okay, guys, I really hope that that does make sense now. 8.1.2, it says which group 1 or 2 use the battery with greater internal resistance. So guys, remember, if you want to know which one has a greater internal resistance, we need to deal with the gradient, isn't it? We need to deal with gradient. So here, guys, steeper gradient would mean greater internal resistance, isn't it? Steeper gradient here. Whichever gradient is steeper would have a greater internal resistance. So steeper gradient here is obviously going to be group 2. Group 2 has the steeper gradient. Use the graph to determine the internal resistance of a battery used by the learners in group 1. Okay, so we just need to use the graph. We know that this represents internal resistance. So internal resistance would be equal to, I'll choose these points here, that point there, and the starting point 12. Okay, So for us to do this, I'm just going to say that my coordinates is 0 and 12, and then my other coordinates is 2 and 8. So here it's going to be 12 minus 8 all over 0 minus 2. And that's minus 2. So that means that our internal resistance is actually just 2 ohms, guys. Internal resistance is just 2 ohms. I know it's a negative 2, but we just deal with it as 2 because the gradient is a negative gradient. So technically it would be minus R, and then eventually you'll get it as R equal to 2 ohms. Okay, guys, anything so far that you guys want to ask, please let me know. I think it's important that you guys know, especially this gradient thing here. The rest of this here, 8.2, not the most difficult thing, right? We should be okay with this. And then just question 9, 10, and then some of your own questions that you guys have sent me. All right, so guys, 8.2, it says in the circuit diagram below, resistor R1 is rated at 6 watts and resistor 2 has a resistance of 10 ohms. Fine. R1 is given, R2, so resistance, voltmeters. Okay. Here's what I do suggest. I'll give you guys like a minute or two. I would suggest drawing this circuit out so that when I'm sorting out the flow of current and where it's joining, where it's splitting, all of those things are going to make sense. So just take a moment and just redraw the diagram quickly, and then we can get to our actual questions here, please, guys. Okay. Guys, I'm hoping you're almost done taking this thing down. I'm just going to start by drawing the flow of current. So going this way here, around, so total, getting to this point, splitting. Some of it's going to go up, some of it's going to go this way, around, there, total again, and flowing around. So current is flowing total, splitting there, rejoining as total, and flowing all the way around. Right. Yes, let's begin with this. So here they've given us the EMF value there. That's nice. It says when the switch is closed, the emitter A reads 1.2 amps and the voltmeter V2 reads 3.8. So here they told us that this is going to be 3.8 volts already. This is 3.8 volts for V2, and this is 1.2 amps already. Now, guys, before I even look at the questions, I want to show you guys what you can fill in from this here. Okay, so what we can fill in is we can say, okay, whatever voltage we're going to have in this branch is going to be the same as the voltage here. So voltage on this right-hand side branch, on this side, is going to be what? Simple. Voltage is just going to be I of 1.2 times the resistance of 10, so that's 12 volts. So we have 12 volts here, and we have 12 volts there. So immediately we can figure that out. We can also then figure out what is our current flowing here. What is our current flowing there? So our current in R1 is going to be how much? Here we're dealing with power. So power is equal to VI, right? So power is 12 volts. Voltage, sorry, not power is 12. Sorry, power is 6. Power is 6. Voltage is 12, and we're looking for a current value. So we're just going to divide by 12, and we're going to get that as 0.5 amps. All right, we're just going to get that as 0.5 amps. So here we have this as 0.5 amps. Done. What does that then tell us? That tells us that our total current flowing through the entire circuit is 1.7 amps. That's our current flowing through the entire circuit is 1.7 amps. So that is, without us actually looking at the question, it's just things that we could see immediately from this particular circuit. All right, let's go and answer the questions. So question here, it says explain what is meant by the term the EMF of the battery is 18 volts. So EMF of the battery being 18 volts means that the battery has an output of 18 joules per coulomb. It has a maximum output of 18 joules per coulomb. That's what it means. Okay. So here it says, if the internal resistance R is 1.29, calculate the resistance of resistor X. Okay, so this is 1.29 ohms, and they want us to calculate the resistance of resistor X. We didn't even need that. Honestly, we did not even need that. All we had to do is now we already know that the current is 1.7, the voltage is 3.8. Easy stuff for us. So now we're going to say that resistor X is just going to be voltage over the current of 1.7, and we're done. So 2.24, yeah, I'll take 2.24. 2.24 ohms, done. What they wanted us to do here is actually use the EMF is equal to I into big R plus small r formula. But I'm showing you didn't even have to do that. If you wanted to do it that way, you could. Okay, then it says, yeah, that switch S is now opened. Okay, so now this is where everything changes. Switch S is now open. So immediately, if switch S is now open, this all changes. These values are gone. All of these current values changes, all the voltage values changes, everything changes. Here, our current will simply flow like this. This whole piece here, obsolete. That whole piece, obsolete. Now, what does that mean? If we're removing a parallel branch, we know that total resistance increases and total current decreases, right? That's what we're supposed to know. That if we're removing a parallel branch, total resistance increases, total current decreases. Okay. Now it says state only increase, decrease, or remains constant. So V1, what will happen to our voltmeter V1? Let's see. V1, remember our total resistance is increasing. Which means that our potential difference at source should also increase, right? Potential difference at the source should also increase. Because that's what V1 is. V1 is potential difference at source. What is going to happen to V2? Where is V2 here? Now, V2 now, basically we're going to have less current, right? We're going to have less current flowing here. So for us to find out what this V2 value is going to be, its voltage is equal to I times R. Now the resistance is constant. Remember that this resistor is not changing. The resistance is constant. But now our current is decreasing. So if the current is decreasing and the resistance is constant, then obviously our voltage value there is also going to be decreasing. So V2's reading is also going to, I shouldn't say also, V2's reading is going to decrease. So this one, decrease. Done. Okay, guys, this is where we're going to stop. 8.2. We're going to have just a little break for about half an hour, and then we'll come back and we'll sort out question 9 and 10 and some of the questions that you guys have sent me. Yeah. All right, guys. It's the same login code. All of those things is still the same thing. Yeah. So just take a half an hour break. We'll start again at 11. Yeah. Where we need to finish and question 10, and then we have 3 or 4 questions that you guys have sent. Nasser, I think you sent one, and then I think Radia, you sent one as well. So let's get through this here. Question 9, it says, the diagrams below illustrate a generator with a rotating coil between magnetic poles shown in a number of different positions labeled A to E. Fine. It says the coil is rotated clockwise at a speed in a uniform magnetic field. Fine. And we know it's a generator, so we know it's the right-hand rule. Okay. 9.1.1, it says, on which principle is the working of a generator based? We know this, guys. We know this. We know it's always based off what? Electromagnetic induction. Right, so that's always based off electromagnetic induction, last year's work. 9.1.2, write down the energy conversion that takes place while the generator is in operation. So when the generator is in operation, obviously it's mechanical energy to electrical. Right, mechanical energy into electrical energy. Right, 9.1.3, guys. 9.1.3, it says a student states that the diagrams illustrate an AC generator. Give a reason why the statement is correct. Because this is an AC generator, definitely an AC generator, but why? Because we see that we have, okay, we have two rings here. We have slip ring and slip ring. It's probably better to put it in. That's slip ring, slip ring, slip ring, slip ring. So we have slip rings, which means it's an AC generator. And this is because of the slip rings. Okay, that's just it. Right, so slip rings, if you can say, I don't know, but they'll all need brushes, so it's fine. So just slip rings is okay. 9.1.4, sketch the graph to show how the induced EMF of the generator varies with time. Clearly indicate positions A, B, C, and D on the graph to correspond on the diagram. Okay, now guys, please note that when the coil is flat like this here, when the coil is flat like that, then what you need to know is that it's going to be at its maximum. So it starts off at its maximum, and then basically when it gets to a zero position, this is the zero position. When it's perpendicular here, it's like its zero position. This is its zero position. Then it goes below, and that would be this position here. Then it's going to come back up to the zero position, because that's the way the graph would be. Zero would be here because it's perpendicular. And then again, at a maximum would be there. So to draw this out nicely for ourselves, let's go and do this. Basically, we start off with it being like this. And remember, starting off like this would mean that it's at its maximum position, at a maximum, either at the top or at the bottom, but most of the time at the top. Then it goes down, there, and there. So this is maximum position at A. B is where it's perpendicular, and that's the zero. Then a maximum, but in the negative version, so it's at the bottom. Yeah, that's D, and then here that's E, and that's it. That's what it should look like, guys. Done. Obviously, I should put that this is EMF, and obviously this is time. They don't say in seconds, but it's normally in seconds, so I'll just put it there, seconds. Okay. Guys, 9.2, it says here that the graph of potential difference and time for the generator in question 9.1 is shown below. Wonderful stuff. Remember, this would essentially then be Vmax. Okay, it says if the RMS current is 1.22 amps produced, determine the rate at which the generator will transfer energy. So we want the rate at which this will transfer energy. Please note, the rate at which something will transfer energy is power, because power is the rate at which work is done or energy is transferred. So power is also energy over time. So just remember that here we're just looking for power. So what is our power formula? Power formula would basically be VRMS times IRMS. We just need to get what our VRMS is going to be. VRMS is going to be 35.36 divided by root 2. And that's 25 exact. So it's 25 times 1.22, and that's my power output. 30.5 watts, and done. Okay, guys, anyone with questions on this here, please tell me. No, okay. Guys, question 10. Like question 9 wasn't that bad. Question 10, I didn't actually read before, so let's go through it. An electroscope with a negatively charged zinc plate is shown below. The gold leaf is deflected due to the light, due to light charges repelling each other. Okay, that's fine. It says when the plate is irradiated with visible light, nothing is observed. Okay, so when the plate is irradiated with visible light, nothing is observed, basically saying that it's not enough energy. When the plate is irradiated with UV light, the gold leaf collapses. Now, why would the gold leaf collapse is pretty much the question for, like, you guys might be asking yourself, like, what is actually going on here? So when we release an electron, right? When we release an electron here, then that means this piece here is actually going to end up being a little bit more positively charged, and this is going to collapse. So this is now going to collapse because it wants to essentially like reach equilibrium again, and it wants to have the same amount of electrons throughout. So basically this will just collapse there, and then it will start the process again. Okay, so if an electron, let's go through it again. If an electron escapes, then this side will be a little bit more positively charged, and then this will collapse so they can reach equilibrium again, and that's the way it would work. Okay, now it says name the phenomenon observed. Guys, the phenomenon is basically the photoelectric effect. We don't have to think too much about that. That's the photoelectric effect. 10.1.2, explain why visible light has no effect on the gold leaf, but ultraviolet light collapses the gold leaf. Basically, visible light doesn't have a high enough frequency. So you need to know for 10.1.2, let's just write it here. UV light as a UV light frequency is greater than visible light. Therefore, UV light energy is greater than visible light energy. Okay, that's done. All right, that's an obvious thing. We know this. We've known this all the time because you guys have done the radio waves, microwaves, all of those things from previous years. Okay, 10.2, the work function of cesium is this here. So they've given us our work function. It says define the term work function. What is the work function? It's the minimum energy required to emit an electron from the surface of a metal. We know that. 10.2.2, calculate the lowest frequency photons should have to eject electrons from cesium. So basically, here, all we're going to do is we're going to say that work function is equal to HFO. Work function here is 3.36 times 10 to the minus 19. Planck's constant is 6.63 times 10 to the minus 34. And then that's our frequency that we're looking for. $5.07. Oh, no, not just 5.07. Just into the 14 hertz. Okay, so that's our hertz there. 5.07 times 10 to the 14 hertz. 10.2.3, it says calculate the maximum kinetic energy of an electron ejected from cesium by a photon of wavelength that day. So they just want to know kinetic energy if we're dealing with a light source that has this wavelength. So all we're going to do is we're going to say energy is equal to WO plus EK. Energy is going to be HC all over lambda, and we know that WO was the 3.36. That's the work function of cesium. And we are essentially calculating EK. So yeah, H is 6.63 times 10 to the minus 34, guys. C is 3 times 10 to the power of 8. Lambda is 400 times 10 to the power of minus 9. This is 3.36 times 10 to the minus 19 plus the EK. And then we're solving our EK. Okay, and that is 1.61 times 10 to the minus 19 joules. Done. Okay, so guys, that is our kinetic energy of a photon that would have, sorry, of an electron that would have been ejected. This one wasn't a difficult photoelectric effect question. We've done weirder ones previously. But yeah, this one wasn't that bad. All right, guys, let's go and sort out some of your questions that you guys have sent me. And hopefully we'll be fine. All right, so guys, here, these are the questions that you guys, those who sent me questions that we're going to go through. So guys, this one, again, I think Nasser, you sent these multiple choice. Guys, I don't know from which papers they are from. No idea from which papers they are from. Right, so what you need to know, okay, they ask us for 1.10 here, when an electron moves from a high energy level to a lower energy level, a specific what is going to be observed. So basically, it's going to be the emission spectrum immediately, because we are going to be, energy is being given off. Now, let me explain to you why energy is being given off before we do anything else here. All right, so I'll just send you guys this multiple choice. Let me just send it to you guys now, actually, because I will forget. All right, so I just sent it to you guys now. Basically, what you need to know is the way electrons work is probably the best way to start with this. So we'll have the nucleus, right? And let's say we have a circle here. Oh, man. Let's see if this will work. So I just want to see. No. It normally auto corrects, but anyway, we'll just do it the normal way. Sorry about that. Okay, so this is the one piece, and then we obviously have a circle that would be bigger than this. So this will be the next energy level. Okay, so we have our neutrons and our protons all the way in here. So if you think of it like this here, what's going to happen is if you have an electron that is in this state here, this is the high energy level going to a lower energy level. So think of it like this. So this is higher energy level and this is the lower energy level. Whenever we're going to go from a high energy level to a lower energy level, there's going to be a difference in energy, isn't it? Whenever you go from a higher energy level to a lower energy level, you're going to be essentially losing energy. But there's no such thing as losing energy, right? There's no such thing as a loss of energy. When this electron goes into a lower energy level, it's going to release energy this way. So it's going to release energy this way. This is going to be regarded as what? Are we essentially emitting it or are we absorbing? Obviously, releasing means we are going to be emitting this here. And because we are dealing with emission and absorption, obviously our answer here would be A. It's an emission line in an emission spectrum. Now, obviously, if you're going the other way, guys, obviously, if you're going this way here, from a lower energy level to a higher energy level, it means that some sort of energy must have come in. Some sort of energy must have been absorbed so that you could take this electron and put it there now. So energy absorbed would be the emission. Oh, I'm saying energy absorbed would be the absorption. Okay, guys, I hope that makes sense. Any questions that you guys have on that there, just let me know. 1.2, it says an object moving, also this one, I don't know where it's from, guys. An object moving at a constant velocity has a momentum P and a kinetic energy E. What will the kinetic energy of the object be if the momentum is changed to 2P while the mass remains constant? Okay, guys, here I would like for you guys to attempt this. This is what I'll tell you. It says here the momentum is P. Momentum is P. Remember, momentum is made up of mass times velocity. And it has a kinetic energy E, and kinetic energy is made up of a half of your mass times your velocity squared. Okay, so what I would suggest is putting your own values to this here, and just see if you guys can figure this out. All right, so I'll give you like a minute to try and think about this. I would suggest just put easy values to this. For example, make this mass 10, for example, and then the velocity like 2, right? Just see what you get from there. Okay, so if we had this as 10 and this as 2, so we're going to essentially say that P is essentially, your momentum is essentially equal to 20. Okay, then here, for an energy E, you have this as 10 and 2 squared. This is going to be a half times the 10 times the 2 squared, which is also going to be 20. Now we need to figure out, okay, if this becomes 2p for the momentum, okay, so if p is now actually 2p, it means that this must now be 2 times the 20. So 2p is actually equal to 40. Okay, so what must our energy value then be? What must our energy value then be? So energy, so your mass remains constant, right? So your mass remains constant. So your mass is 10. Your velocity is going to be, they want to know what will the kinetic energy be. So that means only the velocity is actually changing here. So here we can say that, okay, 2p, right? 2p, or 40 is equal to my mass times my new velocity. So here, my mass was 10, because this is still representing momentum, times velocity. Mass of 10 times velocity, my new velocity that I'm calculating. So that's going to be 4. So my velocity is 4. Now, if I convert this, if I make this a 4 here, so I have this as a half of 10 times 4 squared, what is happening to my energy value now? So now it's going to be a half times 10 times 4 squared, which is now going to be 80. So now, what is actually happening to my energy? My energy has gone from 20 to 80. So that means I'm dealing with 4 times the energy or the kinetic energy that I was. So that's D. Okay, so I hope that makes sense, guys. If you want me to run through that again, guys, let me know. No, seems okay. All right, guys. 1.5. So this is the last of the multiple choice. Then the other question is an Eastern Cape paper 2019. Okay, so here, guys, they say that which one of the following units is equivalent to a watt. So you need to know a watt is power, and that's V I. Power is equal to V squared over R. Power is equal to I squared R. So here they have it as basically they're telling us that this is I times R. This is nonsense. This is I divided by V. Nonsense. AV. This is I times V. Perfect. This is amps, this is ohms, this is amps, this is volts, this is amps, this is volts, this is amps, this is R squared. Now, here, this actually, D could also be the right answer here. Oh, no, D can't be the right answer. Sorry, guys. This is I times R squared. It's not correct. It's supposed to be I squared R. So that's why C is the only correct answer. Okay, guys. Sorts out of this, we're going to go and do now a Eastern Cape paper. This Eastern Cape paper, it's a 2019 paper. I'm just going to redraw the actual situation, and then we can go through it. All right. So basically, Eastern Cape, I think it's 2019 that I saw. Eastern Cape 2019. Obviously, paper 1. It has this situation. Basically, this object, or this metal sphere of mass 1.5 kilograms is dropped from 3 meters. Basically, it now hits another block, and the block is also 1.5 kilograms. This block moves off. They say that there is frictional, there's some sort of like friction there, or it's a rough surface, and they say eventually this thing gets to a velocity of 6.2 meters per second. Okay, so that's what they tell us here. Now in this situation, guys, let me just make sure you guys take this down first, and then they say that point A, point B, when the ball collides with crate, the collision is elastic. And they want us to calculate work done by friction in moving the crate. So basically, okay, first take this down. Okay, guys, let's go and explain this. So when this crate here is moving, the only force acting on it is actually the frictional force, which is going in that direction. So we want to find out how much of work is this frictional force actually doing. So there's a few things that we actually have to do here. Step number 1 for us is we're going to actually have to do this. We're going to have to find out what is the velocity of this ball at point B. So we need to find out what is the velocity of the ball at point B. So guys, here it's actually really simple. We're going to say that EP at the top, because they said it was actually just released, so the velocity here is 0. Apologies, I should have said that. EP at top is equal to EK at bottom. So here, because there's nothing else, we know that the kinetic energy here is 0. We know that here the potential energy here is 0. Right, so here EP at the top is going to be mass times gravity times height. Here it's going to be a half mv squared. You know what, guys, I should rather get you guys into the habit of doing it like this. Mechanical energy at A is equal to mechanical energy at B, because just now you guys always write that EP at top is equal to EK at the bottom. I don't want that to become a problem. So at A, we only have potential energy. At A, we only have potential energy. So that means here, there's no kinetic. At B, we only have kinetic energy. We don't have potential energy. So potential energy goes there. So here we're going to say that mass times gravity times height. Here we're going to say it's a half mv squared. Mass of 1.5, not that it matters. Height of 3, half of 1.5 times the v squared. Okay, 7.67. So I'm getting a velocity of 7.67 meters per second. So that's the velocity of this particular ball just before it collides with the crate. Just before it collides with the crate. So that's going to be 7.67. 7.67 meters per second, and done. Now, because they say the collision was elastic, it means that before, the kinetic energy before must be equal to the kinetic energy after. The kinetic energy before must be equal to the kinetic energy after. So, in actual fact, it means that this collision being elastic, it would mean this. Our crate, so let me actually write it out. A half the mass of our crate times its initial velocity squared plus a half the mass of the ball times its initial velocity squared should be equal to a half the mass of the crate times its velocity final squared plus a half the mass of the ball times its final velocity squared. Right? This is elastic collisions. We know how to do these things. Now what we're going to do from here, guys, is we're going to say, okay, we're essentially just going to sort this out for the crate. We know that the crate initially was 0, the velocity was 0 before the collision. And then, because it's an elastic collision, let me just go and read this again. Okay, yeah. So they don't specify, but we're gonna assume that this ball after the collision comes to rest for it to be an elastic collision. So we're gonna basically say that a half of the 1.5 times the velocity of 7.67 squared is equal to a half times the mass of 1.5, because it's the same mass, guys. It's the same mass throughout. Is equal to this VF squared, and because everything pretty much remains the same here, VF squared is actually just going to be 7.67. So what we're actually saying here, guys, what we're saying is that this goes off at 7.67 meters per second, that 1.5 crate. So if it's going to go off at that velocity of 7.67 and then it reaches a velocity here of 6.2, we need to find out, okay, how much of friction, or I should say not how much of friction, but what is the actual work done by that friction? So to do that, this is what we're going to say, guys. Let me take this and shift it further down. So we are going to say that work net, let's just figure out that the only thing acting on this crate is actually the force of friction. We know there's still a normal force and gravity, but I mean, there's no actual applied force. So if we say work net is equal to the change in the kinetic energy, then work net is actually only equal to, if we're choosing the direction of motion as positive, that means friction is going to be negative. Because, also let me just do that as one more step, F net times delta X. So this is going to be EK final minus EK initial. This is minus force of friction times delta X. But remember, we don't want anything else. We just want, this is minus force of friction times delta X, which is essentially just minus work of friction. Remember that force times displacement is work. So force of friction times displacement is essentially the work done by friction. EK final, so it's a half times 1.5 times the final velocity of 6.2 squared minus a half times 1.5 times 7.67 squared. And this will be the work done by my friction. We'll just convert it to a positive at the end. And that's minus 15.29. So the work done by friction is just 15.29 joules. And that's that.